Good morning, everyone, and welcome to the Society of Engineering Science. On behalf of the Board of Directors of the Society of Engineering Science and as President of SES, it's my pleasure to welcome you all to this new initiative at SES. SES was formed in 1963, and since then, since its inception, it has served as a platform for scientists and engineers to share knowledge, exchange ideas, promote collaboration on interdisciplinary topics, and push the frontiers of science and technology. It's a unique platform that brings together experimentalists, theoreticians, engineers, scientists. So it has served a very unique role in the evolution of science and technology in the country. In the first 50 years, SES grew slowly and gradually, but in the last 10 years, we have seen a tremendous growth in the society. And it is attributed to the unique platform that I mentioned that lies at the crossroads of science and engineering. And if you look today, the new scientific breakthroughs that are taking place, the new R&D centers that are being established, and the new industries that are emerging, and tremendous opportunities for our students going forward and for the general industrial infrastructure of USA. There's tremendous opportunity that lies there, and if we analyze it, we realize that it is because of the close collaboration and well-knit integration of activities between scientists and engineers. So keeping that in view, this year the Board of Directors of SES decided to have a new initiative with the objective that SES platform should also contribute to reshaping education in scientific and technical fields. So today's event is the main idea of today's event is looking at the academic perspective of the growing confluence of science and engineering in research and education. And we would like to discuss and explore the opportunities for our academic institutions to facilitate a more integrated preparation and training for our student body. And if you look around, we see that the new discoveries, the time for new discoveries has tremendously shortened compared to what it was in the 20th century. So there is an opportunity for our academic institutions to provide the continuous stream of our new generation of students in interdisciplinary areas to meet the demands. Going forward, this event will serve as the academic or educational counterpart of the technical and research discussions that take place at the annual events of the Society of Engineering Science. So the format of today's event is going to be, I will introduce our plenary speaker today this morning. After her presentation, there will be a panel discussion together with the current and past leadership of the Society of Engineering Science. And along the way, if there are any questions from our viewers, the participants, please use the chat box and send me the questions, and I will announce those questions. I will ask those questions to our guest speaker and get her viewpoint on that. This gives me great pleasure. It's my honor to introduce our guest speaker today, Dean Nergis Mavalvala, the Dean of the MIT School of Science. Dr. Mavalvala is Curtis and Kathleen Marble Professor of Astrophysics at MIT. She's a Fellow of the American Academy of Arts and Sciences, as well as a MacArthur Foundation Fellow. She is best known for her work on the detection of ripples in the fabric of space-time called gravitational waves. She is the part of the team that in early 2016 announced the first direct detection of gravitational waves from colliding black holes. She was elected to the National Academy of Sciences in 2017, and in 2020, she was named Dean of MIT School of Science. Today, Dean Mavalvala is going to share with us her amazing technical achievements across science and engineering, and share with us her vision and view on the confluence of science and engineering in our academic programs. So with that, Nergis, I invite you to the podium.
Thank you very much, Arif, and hi everybody. Welcome, and thanks for having me here. So I'm going to share a few slides and um, tell you a little bit about the story of the discovery of gravitational waves. And what I want you to take away from that is that it is squarely a story that could only be written when engineering and science came together, not just in, oh, there's a group of engineers and there's a group of scientists, but came together in a very integrated way. So let me start my screen share and tell you a little bit about that story, after which I will open up to questions and discussion. So let me say that the story I'm going to tell you is the story of LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And it's really about one of the significant scientific discoveries of modern times, which is gravitational waves, and how their detection was, a real feat in integrating precision engineering with fundamental science. I will say that these observatories, the detectors I'm going to show you is the work of literally hundreds of scientists. So please treat me just as the messenger and not the one who's done this all of this work uniquely myself. So let's begin the story with close to the end, if you will, but really it isn't. It's close to the beginning, and that is the 2017 Nobel Prize in Physics, which was awarded for a discovery that shook the world. That was the quote for decisive contributions to the LIGO detector and the observation of gravitational waves. These three founding fathers of the field were awarded a Nobel Prize. So let's deconstruct that a little bit. First, what are gravitational waves, and why was this such an important discovery, and important enough that not only the discovery, but notice the detector, the LIGO detector, was also named in the Nobel citation. So gravitational waves are essentially ripples of space-time itself, and they were actually predicted by Einstein in 1916, but he himself sort of dismissed them as too faint to ever be sort of detectable or useful. And Einstein was kind of right, because when we think about how these gravitational waves are generated, they're generated by astrophysical objects, gravitating objects that accelerate. And so they are generated essentially by cosmic objects, stars that orbit each other, for example. But if you take ordinary stars like our own sun and you put them in orbit around another ordinary star like another sun, the gravitational waves that would be emitted by that system are really incredibly faint. And you need more compact, massive objects like black holes or their lighter cousins, which are neutron stars, to actually have any hope of detecting these faint ripples of space-time itself. And so from 1916, Einstein made this prediction, and then we have to fast forward all the way to the late 1960s and 1970s, where Kip Thorne, one of our Nobel laureates from 2017, made early predictions, calculations that said Einstein is right, they're pretty faint. But right around that time, black holes and neutron stars had been discovered by other techniques. And so Thorne made the early calculations that said, if you have two black holes in orbit around each other, maybe you have a shot of detecting them, and they would have an amplitude of 10 to the minus 21. And this is a dimensionless number, because the way that the gravitational wave amplitude manifests itself to us as observers is as a strain, so as a change in length per length of the space-time itself. Around the same time, the late 1960s and 1970s, our other Nobel laureate, Ray Weiss, who's an experimentalist, said, well, wait a minute, maybe, just maybe, these are detectable. We just have to figure out how we can measure space-time distances, changes in those distances at the level of 10 to the minus 18 meters, or about an attometer, which is 1,000 times smaller than the radius of a single proton. So you can see that back then, in the early 70s, this was extremely audacious and seen as improbable and almost certain to fail. But Thorne and Weiss were undaunted. They met in 1975 and began a campaign for the United States in particular, but this was also happening elsewhere in Europe for sure, to build large detectors that would be capable of making these tiny, these precision measurements at the level of an atometer, with the goal of detecting gravitational waves from colliding, merging, orbiting and then merging neutron stars and black holes. And that sort of gave birth to the concept of LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And so LIGO is essentially an interferometer, and I have a cartoon, an animation of an interferometer on the top right there. And what you see is it's essentially a light source, in our case a laser, that's split into two paths, one path that's orthogonal to the laser and one that's in line with it. And that light in each path reflects off of two mirrors at the end of the light path and then comes back to the beam splitter and interferes. And depending on whether the path lengths between the two paths are equal, and you get constructive interference, which means all of the light interferes constructively, and you see a lot of light at this output at the bottom detector. Or you can also raise the path length to have complete destructive interference, which means that the troughs and peaks of the light waves line up with each other, and the two paths, the light waves, are superposed to give you no light, and everything in between. And so this is the picture you should carry away. This is an animation of the interferometer. As the path length changes, you get a lot of light or no light, and our job as detector specialists is to detect that light and to be able to tell what the path length difference is. Now, there's two problems with this scheme, and this is where sort of the amazing feats of engineering meeting science come together. The first problem you have to solve is that the gravitational wave that's passing by moves these mirrors by 10 to the minus 18 meters, sort of RMS, integrated in a band. Whereas the mirrors themselves, in their natural state, because of all of the vibrational environment of the Earth, are moving by about a micron, so 10 to the minus 6 meters. So that's the first thing you have to do, is you have to reduce the natural motion of these mirrors by a factor of 1 trillion, or by 10 to the 12. And the way that that's done in LIGO is through an elaborate vibration isolation system. The first vibration isolation system is this one on the bottom left, the first layer of it. And that's an active vibration isolation system, which is developed in a collaboration of scientists and mechanical engineering, if you will, and also some electrical engineering and control system design, because what this part of the vibration isolation system is basically a noise cancellation system. You measure the motion of the Earth near LIGO's mirrors, and then you subtract it out by actuating on this payload that's shown over here. And that gives us our first sort of factor of about 10 to the, gets us halfway to our goal, gives us our first factor of about 10 to the 6. And then we take the mirrors of LIGO and we hang them as pendulums, not just as a single pendulum, which is, this is the bottom layer of the pendulum, that's the mirror at the bottom. But then there's another layer of pendulum, which is the round object at the top, and then two more layers of pendulum at the very top that are basically spring blade flexures. And this, because as we all learn in our very first physics classes, a spring mass system or a pendulum system is naturally a filter for motion. What you see is that at the bottom, the mirror moves by about a factor of 1 million less than motion at the top, which is attached to this vibration isolation system, noise cancellation system, which is attached to the ground. So between ground motion and the motion of the mirror, we can achieve that factor of 1 trillion. That's the vibration isolation system. And then that does you absolutely no good if you don't know. You can make this mirror really, really still. so still that the Earth's vibrations aren't disturbing it, but gravitational waves passing by will move it. And that does you absolutely no good if you don't know how to measure those tiny motions. How do we know the mirror is moving? And there comes our other uh, sort of significant factor of a trillion, and that is the precision optical measurement. So we do the measurement, as I showed you, by interferometry. And the way you can think about this is that the wavelength of the light is the tick marks on our ruler, right? So wavelength of the light is our meter stick, and the wavelength of the light is the tick marks on our meter stick. So the light that we use for a variety of technical reasons is 1 micron light, 10 to the minus 6 meters is its wavelength. And so you can see the monumental task ahead. We want to measure a precision of 10 to the minus 18 meters, which is a trillion times smaller than the spacing of the tick marks on our ruler. And the way we get around that is, of course, by doing a tremendous amount of averaging, by using many photons and averaging over the fluctuations in the spacing of our tick marks. And to do that, which for people who are familiar with optical measurements, means doing a shot noise limited measurement. And we do that by starting off with a very powerful laser. Our laser is capable of putting out 200 watts of continuous wave light at 1064 nanometers. And then by a series of tricks by placing mirrors inside of the interferometer itself, here are the 4-kilometer long interferometers of LIGO shown on the bottom right, a detector in Louisiana, and the top left, a detector in Washington State. So 2 detectors in the US. They're 4 kilometers long. The light bounces multiple times between mirrors in those 4-kilometer arms. And by doing those tricks, we can have almost a megawatt, 750 kilowatts of optical power circulating in the interferometer. And the averaging over all those photons per second gives us a measurement of the mirror displacement at the level of 10 to the minus 18 meters. Now, this effort has been funded in the US over many decades by the National Science Foundation, which has been sort of the lead funding source for the US effort. Our third Nobel laureate, Barry Barish, was the one who was associated with having built these observatories. So that was the state of affairs. In 2015, we had these detectors, and not just LIGO, but there's a global network. The 2 LIGO detectors are here in the US, but there is a detector in Europe called Virgo, a 3-kilometer long detector. There is a 4-kilometer long detector being built in India called LIGO India, which is a LIGO detector placed in India, and there is a Japanese detector called Kagra. And this was the global network of detectors. LIGO were the only 2 operational in 2015 when the first detection of gravitational waves were made. And here is a nice cartoon of what happened. Here are 2 black holes. As they orbit each other, these black holes are radiating away gravitational waves because they are so compact and massive. And the energy carried away by these gravitational waves comes from the orbit, which means the orbit is shrinking. These black holes are getting closer and closer to each other. Now, you can see that something like the Earth-Sun system doesn't do that because we're just not radiating away enough energy in gravitational waves. We're too light, basically, the Earth and the Sun, for example. So here then is the movie. 2 black holes collide. These black holes radiate gravitational waves. The gravitational waves then travel across the universe in a very literal sense. These were over 1 billion light years away from the Earth. But sure enough, 1 billion years later, these gravitational waves arrived here on our Earth. And in a highly exaggerated way, you can see what they did was they changed the space-time distances between points on the Earth, and in particular between the mirrors of the LIGO detectors, highly exaggerated here. And this was in fact the signal that was recorded. And so what you see here is time on the horizontal axis and amplitude of the wave on the vertical axis. And this is a And these bumps and wiggles that you see are the gravitational wave from these two black holes embedded in the noisy data stream of our detectors. And you see a few remarkable things. At the time that the two black holes collided is the moment of maximum amplitude of the wave. That's the right here. And at that point, the wave had an amplitude of 10 to the minus 21 in strain. So it's an enormous check mark for Kip Thorne. He had predicted this from his early calculations, remember, in the late 1960s and early 70s. If you ask how much the mirrors of LIGO were moving at that moment, that translates into a motion of a few times 10 to the minus 18 meters. It's an enormous check mark for Ray Weiss, who told us in 1972 exactly how to build these detectors. Exactly is an exaggeration. He gave us a very good design for it, a preliminary design, we would say in engineering speak for it. And then here we are decades later having built this instrument and made this first measurement of gravitational waves from two black holes that were colliding. And embedded in the signal, we could even tell a lot about the black hole system. We could tell that the black holes had masses that are about 30 times the mass of our own sun. At the moment that they collided, and this is something that is really, you have to hold on to your seats to wrap your head around this. These 30 solar mass objects were moving at about half the speed of light when they collided. So it's an extremely relativistic system. The distance from us to the source was 1.3 billion light years. And what we could tell that the new black hole that was formed from the merger of these two was 3 solar masses lighter than the sum of the two parent black holes, which means 3 times the mass of our sun was radiated away as gravitational waves in this collision. So in the meantime, we've since those first discoveries, LIGO has and its partner observatory Virgo has made detections of nearly 100 different types of gravitational wave sources, including collisions of neutron stars and of black holes where we don't know why they're so massive, and there are lots of mysteries. This is one of the beauties of science, which is why I think of myself as a scientist engineer, which is that I love that when science makes a discovery, it's really only taught us what's the next question to ask, and engineering enables us to be able to make those discoveries by designing instruments such as this one. So let me just close by giving you a few really interesting things that we had to integrate to make LIGO work. I told you about the vibration isolation system. We needed 12 orders of magnitude of suppression of vibrational noise. LIGO's vacuum system to this date is the biggest one, 20,000 cubic meters of vacuum that operates at 10 to the minus 8 torr hydrogen. The laser is the highest power laser that we know how to make whilst achieving its noise performance for both its frequency fluctuations and its amplitude fluctuations. There are over 3,000 controls and feedback loops that operate LIGO. There is an enormous amount of thermal engineering because thermally driven fluctuations also shake our mirror. There's an enormous amount of material science that goes into making literally the most precise mirrors that have ever been polished and coated. We design our own low noise, high bandwidth electronics, which are both analog and digital. We have embedded digital architectures for doing things fast enough. We have high performance computing for data extraction, storage, and analysis. And then not to be taken lightly, even just calculating what Einstein's theory of relativity would give us for signals from these collisions of black holes. We have very, very sophisticated numerical algorithms that involve multi-scale math, physics, and computing. And that's what we've had to put together to reach this unprecedented precision. And I'll put this into numbers. I don't have any intention of you following any of these numbers other than to tell you that this is indeed the most precise position or optical phase measurement ever made. It has extreme requirements on the lasers, on the positions of the mirror, on the angular controls of the mirrors, on the materials properties of the mirrors, on the surface roughness of the mirrors, and literally thousands of other things I won't tell you about. But what I want to put this up here for is to tell you that in the end, each of these color-coded things is a subsystem, and none of it could work without systems integration, which is really every subsystem works well on its own, but it also has to interface and work with and meet its own specs when it interfaces with 100 other subsystems. So I hope I've convinced you that LIGO could not have been built without a real coming together of science and engineering. The excitement around this experiment is that we've really launched a new way of looking at the universe. We've made these first detections of gravitational waves, directly observing them. We've confirmed that Einstein's predictions were correct. We've seen these collisions of black holes and neutron stars observed in real time, which are telling us a lot about the properties of these objects and indeed the properties of the universe. And for someone like me who has spent my entire career designing and building these precision instruments, it's also really nice that the damn instrument worked at the atometer precision that was needed. And that's the story I wanted to tell you all today. But looking to the future, this is a completely new way to look at the universe. We can now use gravity instead of light. And this is a tool for really unimagined new discoveries. And it was entirely enabled by science and engineering combining to realize something that was really improbable, and this improbable technical feat that we call LIGO. So that's sort of the scientific story I want to tell you. I want to close my remarks just by giving you a little bit of things to ponder on where we are, not just in the research space, but also in the education space with thinking about engineering sciences. So I think one of the things that troubles me as someone, in my own research group, I supervise students who come from physics departments, graduate students who come from physics departments, from mechanical engineering, from electrical engineering, and even from aeroastro departments. And so I have been really surprised by how uncommon integrated engineering sciences curricula are. And so for me, as a PI, I have to sort of teach my students those parts of the trade they don't know. The engineering students have to learn the physics, the science, the motivations. The physics students have to learn the engineering and the systems and design side of things. And this comes about in part because most academic institutions are organizationally siloed. There are departments and faculties and schools, and they're organized that way. I'm learning in my role as dean, in part, of course, because those are the ways in which resources can be allocated. But it comes at a tremendous cost to our students and our enterprise when we can't, when we don't have the ability to train our students in this truly interdisciplinary way. I've also been part of many debates on depth versus breadth, where there's some idea, in my opinion, wrong idea, that when you have interdisciplinary training for students, you have to give up on them learning anything in depth because they have to have so much breadth. And I think this is a very solvable issue. And I will say that certainly in all of my work, both at MIT and also in the national sort of STEM ecosystem, there is a growing demand for interdisciplinary opportunities, especially from training. Students and postdocs really want to be able to do more interdisciplinary things. And there is the bottlenecks come really from what department do they belong to, who funds them, even for things like grant proposals. When I have to fund, some parts of my research, I have to go to multiple, parts of my funding agency, which is NSF, to sort of show that this is interdisciplinary and needs more than just one narrow a program to fund. So I'll leave us with these final thoughts about about what kinds of degree requirements could we think about education, what are the foundational things that every student should know. I do believe that the foundation for engineering is science. And so, having a good foundation in mathematics, physics, chemistry, and biology is important for every engineer to know. I since I span both worlds, I say this with great affection. I think creating majors that have more flexible requirements so students don't have to only study one thing, thinking about how to use minors and concentrations, and just having more interdisciplinary programs is, I think, going to be part of the thing, the way that we achieve these goals. So I will stop here now. I hope, and I'll hand back to Arif, who will introduce our panel, and I'm happy to take questions, depending on how much time we have, etc.
Thank you very much, Nergis. This was a very inspiring talk, very inspiring work, and you used a perfect example where you brought in the theory, the experiments, and the engineering together to highlight how important the interdisciplinary work is for the future of revolutionary breakthroughs in science and engineering. So, and you also touched upon the organizational structures that you mentioned that are somehow in silos, and they're doing fantastic in their own domains. But as we look into the future and we see that it's science and engineering coming together and students coming together, and that is where major breakthroughs lie. That is where the future growth of the American industry lies. And American industry has always been high tech, and the turnaround time is shorter. So the need for a well-integrated level of preparation for the students going into the future is going to be very, very important and critical. And the organizational structures that were in 60s, 70s, 80s, they've served us very well so far, but the needs and demands of the 21st century have changed. So that is what we are going to be discussing. So thank you very much for your very inspiring talk. And I'll now go to the second part of our format here. I'll take a minute to introduce our panel. We have the three past presidents of SES who share the same vision as I've been discussing here. Vicky Nguyen from Johns Hopkins University, and he was president of SES in 2020. Marcus Boeller from MIT, he was past president in 2019. And Glacio Polino from Princeton, and past president from 2018. So with that, I welcome you all now to the panel discussion part, and I open the floor for discussion with Nergis. And let me also announce for our viewers, if there are any questions, you can send me the question through chat, or you can also raise your hand, and Bethany, who is managing this event, she will put spotlight on you so that you can ask the question. So you have both the options open.
Perhaps I can just start and say thank you, Dean Nergis, for the talk. It was really impressive. And I learned a lot, actually. I didn't know much about gravitational waves, so it was really great. And I really also appreciate the last few slides that you put up. At Johns Hopkins in the School of Engineering, I think we're undergoing, or we're in the middle of this conversation about education, streamlining the educational requirements of engineering. And there is a lot of debate. And so you're mentioning about the debate of depth versus breadth is something that is discussed constantly here. And I think MIT underwent that, at least in mechanical engineering, underwent that conversation a few years ago as well. So yeah, I think it's a very timely discussion.
Yes, thank you, Vicky. I agreed. I would love to hear more from the panelists too about how to tackle the depth versus breadth discussion, because it comes up a lot. And my answer in the fields that I know well is that you acquire depth on the job, you acquire breadth in learning how to think, which is what education is about.
Yeah.
So that's one of the ways that I have dealt with it. But for many of our students who go on to graduate school, that's fine. But for those who enter the workforce right away, we also have to be responsive to their needs.
Yeah. I mean, I'll give you some perspective. I work in a very multidisciplinary field. I've got joint appointments, secondary appointments in ophthalmology, as well as material science, and I've been trained mechanical engineer. And so I've had to learn a lot of, I guess, acquired a lot of information on physiology, on biology, on the job. And I remember when I interviewed at Hopkins a long time ago, I was asked by one of the interviewers, which students would you take, for your biomechanics? Would you admit biology students or would you admit mechanical engineering students? And I had to think about it for a little bit, but the answer came really easily for me then, which is I definitely would want to admit mechanical engineering students. I want to educate mechanical engineering students, and the stuff about physiology and biology they can acquire on the job. But and perhaps I still believe in this. You need the depth in a specialty area so that you can contribute to a multidisciplinary topic, at least as a researcher. But I also know, when we're trying to serve a broader set of students who go out into industry, that kind of philosophy may not serve them well, right? So if you're going to be a mechanical engineering undergraduate, do you really need 3 courses in thermal fluids to be a practicing mechanical engineer? So I think it's a very nuanced debate, and my views have slightly shifted over time. So I can see the need for streamlining education to tackle really difficult topics like sustainability, right? Recycling. If you want to go in and work in the recycling to improve recycling methods, you really can't just know about one discipline, right? You need to have an understanding of a bit of materials and energy systems and a variety of things. So yeah, I think I love to hear everyone else's perspective as well.
So Nergis, if I may ask, so you mentioned about academic institutions and how they can. So from your point of view, what are the commonalities between, let's say, College of Engineering and College of Sciences that we can leverage upon? Because commonalities will provide the common platform where you can bring resources from both sides to cover the interface between science and engineering disciplines. So from your point of view, what do you think where academic institutions can take advantage of their existing infrastructures?
Yeah, so I think that's a very good question. I mean, I think those structures are, again, they're necessary as organizing principles, but I think the way that I have come to think about it is that we have to have, it's not like we cannot have walls or barriers, but they have to be much more porous. And what I mean by that is that, so for example, one of the very enjoyable things that I do as Dean of the School of Science is at MIT is I work very closely with the School of Engineering, and we are working actively on a joint fellowship program. So there are students who don't have to be siloed by where their funding is coming from if they want to do something cross-disciplinary across schools. And so we use our resources to make those walls more porous. That's one way to go. And I actually predict that in the future, these kinds of programs are going to be more and more in demand. So we say, okay, right now we're just going to say, we'll provide 5 students a year with this opportunity. I don't think it's going to be anywhere near enough in terms of what we have heard from what our students would be like to do. I think similarly also on the at a big research university like ours, I think even on the faculty side, there's a lot of hunger to do work jointly, and I think right now it's done very much in the way in very ad hoc ways. Two people get together in a sort of a bipartite way. But I think we have to find structures to facilitate that, and I think dedicating resources to that. So we have a few resources dedicated to faculty who want to do something cross-disciplinarily. But I think ultimately it's going to be along the lines of what Vicky said, which is that I think we have to really think about who are our academic programs serving, and what should they look like. And they may not be a one size fits all, and we've learned that even within disciplines. So my own home department is physics, and about 20 years ago, the physics department at MIT revamped its curriculum to offer something called the flexible degree major. And it basically gave students more flexibility to create a physics major by using subjects from other departments. So you can have a biophysics major and you can do some biology instead of physics, rather than you do all the physics that was required and then do more biology. And that's been hugely successful. The vast majority of our majors today are flexible majors. They're not the traditional ones. So I think we're more and more going to have to move in that direction as educators.
More porous boundaries and more flexibility in systems.
Can I ask a quick follow-up?
Yeah, sure, Marcus, please.
So, Nergis, a really wonderful talk and a great discussion. I had a question on the students. What kind of profile of students do you see that actually take on, especially the science engineering? I've seen lots of students doing cross-disciplinary work between engineering departments, right? But then if you go to, let's say, work with you on gravitational waves, and then you work in aeroastro, and that's a really big stretch. So what's your insight on the kind of student profile you see, or what their responses are, and what kind of things can we do as educators in terms of advising, mentoring? Because students come in, you have an idea what they want to do, and then we play a very big role in that kind of, hopefully a positive role, and in playing an active role in advising them, undergrads or grad students, I think both. I think there's a role to play here and telling them about opportunities, because they don't really know all the things that are out there. I think you've done a great job in connecting these disciplines, but sort of these two things, students, and then how do we help the students to see these opportunities?
Yeah, it's a really good question. So I will admit that many, not all, I would say about maybe a third of my engineering students have done undergraduate degrees in engineering sciences. So they know this exists, so whether they're coming from Penn State or Caltech, or so they have some idea that this is possible. The way that I have managed to do it is, of course, to work with especially graduate students who are working on doctoral degrees mostly. I need a partner in their home department. So that's how I have managed it, is I have partnerships with faculty in these departments. They know what kind of students I'm looking for. I let them know when we have openings, and we always do. So there's almost never a time when we say no to students. And then I basically look for students who are passionate about the science as well. And I was one of those. I was exactly one of those who was at a crossroads of, am I going to be a physicist or am I going to be an engineer? And I will just say, upfront to everyone, I decided to be a physicist because I thought, as a physicist, I can always be an engineer. As an engineer, I can't always be a physicist. At least as education and practice goes. So that's how I had to choose. But if today I would be one of those students who wouldn't have to make a choice if there were programs that did that. But yeah, so that's what I look for. I will say I look for that in my physics students as well. My physics students have to love to build things, because yes, we are doing physics and we're studying the universe and we're uncovering literally how the universe was born and looks today. And these are the big questions that excite us, but the everyday work is make your goddamn circuit work. So it's got to, you have to have that mindset.
Thank you.
There's a question from the audience here. It is from from David Owen. And how do accreditation requirements for engineering departments constrain the goal of a broader undergraduate curriculum?
Perhaps former department chairs can talk about this more, but from what I understand, if you're talking about ABET accreditation, I think you get to define your criteria as a department to get accredited, right? There's no, ABET doesn't say you have to have X number of courses in a certain discipline for your program. But again, having not ran the ABET program before, I don't want to overstep my bounds.
I can say I can say a few words about this, and I mean very briefly. I mean it's a long story, but I mean this is actually a great question that David you're asking, and Vicky. This is actually, in my experience, one of the really big issues in innovating for engineering curricula. And I think at MIT, what we've done to the last, I would say, 5-10 years, is going to create two options, two tracks. One is a more traditional, ASME or ACE accredited program, and then you might have another one that is not accredited or maybe accredited by flexible. I think ASCE is the accrediting body there, so it's a more flexible one. And that's a pathway that some departments have chosen. At MIT, for example, some departments have actually not chosen to go with the traditional accreditation like CEE is, it's chosen not to do that anymore and just go with a flexible degree. But that's a big decision, and a lot of the stakeholders, like alumni and industry, like Nergis, you mentioned, we have to keep in mind what the students want and where they're going to go. I mean, that's a really big discussion, and I think there's really, that's all I want to end. There's a disconnect between these accrediting bodies, which are basically run by universities, have a very different audience and clientele than, let's say, MIT, Harvard, Princeton, Caltech, and all these top tier universities that are really going into the space that we're talking about here. Others might follow, but it's going to be maybe a few more years until they get there. But there's really right now kind of a binary choice a lot of times, and that's unfortunate. I wish there would be more flexibility, more communication, right, between these accrediting bodies and the places like MIT. Because if we all give up being part of these accrediting bodies, we're going to have a two-tier system. We're going to have the rank 1 universities being accredited, being not accredited, and the rest is, and we're going to lose this kind of leading voice that we can play as places like MIT or places like this. So I think that's a little bit unfortunate, but maybe others have more thoughts on this.
But Marcus, it might be okay, right, to have the approach where I think most universities, they will be accredited, but it may not make sense for every university. And then we can have a diversity and intellectual diversity around the spectrum of knowledge and universities that are available, right? And that's the way I see it, that accreditation for some universities is a must, make a lot of sense, but is not one formula fits all. For some universities, accreditation may not make sense. And I think having both scenarios is intellectually stimulating, is good, provides a lot of opportunities for students. And I think at the end is something good.
Yeah. I generally agree with that. Oh, sorry.
I personally like the idea of the two tracks. And it just gives students a lot of choice. At Hopkins, it's interesting. We've had two tracks forever. We've had an engineering mechanics track, a mechanical engineering and mechanical engineering degree. And you would think that the engineering mechanics track would be more popular because that's the trend. But the mechanical engineering degree, which is more restrictive, has always been overwhelmingly more popular. So, and the students that kind of go through and we do our exit interview always say when they leave, I guess perhaps they don't have the perspective that they appreciate the depth that they've received from our curriculum. I think that brings me back to the question. I'd love to have a discussion here focused on undergrads. How do you advise the undergrads, in terms of when you have such a flexible program? Because they don't have, they may not, we like to think that they know exactly what they want to do when they graduate, but they don't, right? They don't have that breadth of experience, and they they shouldn't know exactly what they're going to do when they enter the program. That's kind of like the privilege of an undergraduate education. So how do you go about advising students when you have a lot of flexibility in your program?
I think a good question, Vicky, that you're posing, and I think undergrads in particular, because they're going to be our future grad students, but I think it is at the institutional level also that we need to, whenever we look at interdisciplinary programs, they are not easy to even evaluate. You need to have multiple measures of evaluating them. Some of them are going to be quantitative, some of them are going to be qualitative, and some are going to be based on pure expert opinion. So whenever that is a fundamental thing with the interdisciplinary education or flexibility, whenever we bring flexibility in, and that will go, I think, both in the undergrad level, grad level, and I think also to the level of faculty and administration. So I think this is a question that will permeate all the way through to the top. So taking the lead from your particular question, let me ask Nergis your point of view, that let's say if there are institutions that are trying to follow along those lines and they believe in multidisciplinary, interdisciplinary education and programs and portfolios for their students, what in your opinion could be the markers along the way, or the you can say milestones, or how can they check the matrix of success that they are walking along that line of having more interdisciplinarity, more porous boundaries, less rigid structure? What are the metrics of success from an administrative point of view?
Yeah, I think those metrics of success would be, first of all, it would be on the administrators of these programs to measure, that, not the students. But the students, I think for me it would be, what are their learning outcomes, and what are their career outcomes. These are the things that students come to university for, right? They come to learn, and they come to as a stepping stone to the next thing they want to do. And so that would be where I would look. I think I would require input from the alumni of these interdisciplinary program. It would also require input from their eventual employers, whether they went on to further study or they joined the workforce. But I think those would be sort of the places where I would look to measure success. And there's one other thing that I would add to that, and that is, what were their opportunity costs in doing something so interdisciplinary? Obviously, a student has to give up on something else. Maybe this is the death versus breath debate again. And was it all right? Did it work out okay? So I'll say, from the perspective of my physics undergraduates who follow this flexible degree as opposed to the traditional degree, more than half of the graduating class still goes to graduate school in physics, to PhD programs. And what we have heard back from the vast majority of them is that having a flexible degree has no measurable consequences, because the things they might not have done as undergraduates at MIT, they still have a chance to fill in on when they enter their graduate programs. And for those who don't go to graduate school right away and follow other careers, they are extremely satisfied with having had the flexibility to do other things. Some of our students do a lot more math when they do the flexible physics degree, and they get a degree in mathematical physics, and then they go off to. So I think those are the ways in which I would measure. And I'm sure there are others I haven't thought about.
Thank you, Nergis. There's another question from the audience. It is from Professor Oral Bickerstaff from MIT, and he's asking, nowadays, interdisciplinarity in our research is a must in view of the complexities of problems, and yet generally this reality has not been realized in the profession or in educational systems. What might be the main factors for that, and what can be done to effectively effective education approaches for the future? So what have been the hindrances in the past to be able to integrate, and going forward, what could be the effective approach?
So I'm going to just take a tiny piece of that question because it's also related to a question that was put in the chat by Azadeh. And that is really, if we really want to be interdisciplinary, we have to update our own processes for how we measure the success of our junior colleagues, for example. How does tenure and promotion work when you've done something really interdisciplinary as well? So I just want to put out that that is an absolute work in progress. I do not think we're there by a long shot. And that is a process of educating our colleagues who sit on promotion and hiring committees, et cetera, but it's work that has to be done if we want to go down this path of greater interdisciplinarity. So I'll stop there and let my fellow panelists take the rest of the question, but I did want to address that one piece.
Ignacio, would you like to take on that question?
Yeah, maybe I can offer a thought here regarding the interdisciplinary approach. And I see a difference, for example, in the students, let's say the education, the learning phase, and then the research. And for an effective interdisciplinary approach, I think that it's very important to concentrate on the fundamentals. And then if a student that is in engineering, civil, electrical, mechanical, that needs to learn, for example, more about biology, physics, chemistry, and so on, to concentrate on the fundamentals, because the fundamentals, they scale, they translate. And then later, if you are interested on the boundary of knowledge in the field, then you can learn that by yourself, or you can take specialized classes. But I think this also relates to the question that Nergis put for us about depth versus breadth. And I think emphasizing on the interfaces between fields. I think a lot of the interesting aspects are on the interfaces between the areas, among the areas, and emphasizing on the fundamentals would be a very successful approach. For example, this semester, I just had a unique experience here at Princeton. I advised a final thesis project, undergraduate in astrophysics. And it was really a great experience and promoted a lot of good things. And I learned a lot too in astrophysics. And I think the student learned a lot about differential geometry, origami, and deployable systems that can be used in astrophysical applications. And that was a great experience. And in this experience, we always emphasized on the fundamentals. For me to learn a little bit of astrophysics, concentrating on the fundamentals, and for the student, concentrating on the fundamentals in engineering so that we could do something useful.
Can I follow up on this point real quick? So it was a great point that you made, and I completely agree with fundamentals. I mean, one thing, and I think there's even a comment in the chat right now, I can't read it all, but I think we might want to think about more than 4-year education for that purpose. I think it's really dangerous if we're thinking about, okay, we're going to cram a lot of that stuff in 4 years and really fundamentals important. So in my view, I think we might want to think about maybe, 4-year undergrad, but then also have a master's degree in something that really lets you cut across a little bit more. I mean, that's my personal advice. I usually tell my advisees this, I said, don't rush it and really spend the time in fundamentals. They should be flexible, I think, right? So you can choose what kind of fundamentals you want to work on, and maybe different for different people. But I agree, the math and basic physics and mechanics and these kind of things are really important, and you can translate them. But yeah, maybe the master's degree or an MNG degree, and we have MIT with these 1-year master's degrees here. I mean, those are great ways to do that. And that's something, I think there was a comment I think Gary Seidel, or somebody asked about that as well in the comments. I mean, Arif can follow up on this maybe, but that seems to be something we should think about, because we can't just add more and more. But then, of course, there's new technology. I think you can learn a lot more effectively, efficiently, perhaps today. That's to be shown or not, I don't know. But perhaps there are better learning way. There's more information available at your fingertips, right? I mean, than 20 years ago. perhaps that helps, but there's a limit, I think. And I think really there's no shortcut to learning the fundamentals.
Thank you, Marcus. Thank you, Glacio. There are some questions, Nergis, in the chat box. If there is any question that that you'd like to, respond to, please take this opportunity.
Yeah. If I may, there is a very good question here from Azadeh Shadeh from Iowa State University.
Please go ahead and you can ask that question.
It's not risky for junior faculty to do multidisciplinary research, as most funding agencies have focused programs, and also for the tenure promotion process, they might face problems. It's a good question.
I mean, I can totally agree. This is actually very risky. I mean, we always say, do it, but it's actually risky. And the reason is simply, I think the evaluators may not be able to make that stretch, right? And I think that's something I've seen. It takes a lot of work on the evaluating bodies that are doing the tenure cases and so on. And I think we're trying really hard as a community. And I know at MIT, we're trying really hard, but it is difficult because we just don't have the expertise. And there's if somebody's right in the core in the middle, there aren't a lot of people like that. And we tend to be biased to what we know, we've seen. And that bias actually is really very, very hard on these candidates. And it's a hard truth, I think, because like the question is exposed. There's a lot of push to this from funding agencies, but I think we have to do more work on the other end, right? In hiring as well, and in promotions and so on, to make this actually successful.
And Marcus, following up on what your comments, I think this is very, very important. This is where change in mindset also at the academic level also is needed. I was chair of the P&T in the department, and we had to look into, traditionally we were evaluating people based on civil engineering portfolios, but then when multidisciplinary, interdisciplinary came in, we had to broaden our perspective to that. And I think this is an exercise that all departments will need to do, colleges will need to do. It's a thing that will permeate from grassroots level all the way to the top. To be able to have a well-integrated interdisciplinary programs which are successful in producing the output, as Nergis mentioned, that what is the net product from these institutions and how they are leading the industry, leading the universities. And we agree, I think the panel agrees that something needs to be done. There is a great opportunity for us, for the academic institutions to step in this area, as well as and we see that there is a tremendous growth potential for the future for our industry and for the American leadership in the industry to produce this kind of product from academic institutions. So again,
if I may, this also relates to the point that Nergis pointed out about the organizational silos that we have. And I think the challenge would be, maybe the silos, they are so strong from history, maybe they have to exist, and they do exist. But the question is, how can we make the silos less silos and more inclusive, more appreciative of other areas rather than being so segregated? And we can see even the places that try to go beyond the silo, right? There is some difficulty, especially when pragmatic aspects come into the picture, like what you pointed out, Aref, like promotion and tenure and so on. But I think for the future, this will be the idea, how to make the silos less of a silo and more of an appreciative unit of other areas of knowledge in a tangible fashion, not just the talk, but tangible.
Glacio, you made a very good point. And I think, as Nergis mentioned, that porous boundaries, joint degree programs or cross-disciplinary education, faculty, promotion, assessment, hiring, all that, maybe partnership with industries, that will create an environment, but that environment needs to propagate all the way from top to the bottom. And some success metrics need to be evaluated so people can get encouraged that after some time they can evaluate and how they are going along those lines. Nergis, for the last couple, I'd like to give you the last, so you can make your last statements and your message for the community.
Oh my goodness, I get the last word here.
Yes.
I actually think given the hour, etc., maybe just a warm thank you to all of our panelists and to you for organizing us, and for all the participants for your ideas and questions. So thank you very much, and I will leave it at that.
Thank you, Nergis. I want to thank everybody for being here, for participating. I want to thank the panel, and with that, I thank you all, and thank you for being with us today.